All right, so let's talk about the ultraviolet catastrophe, okay? Do you have any questions so far?
No.
Okay, so what is the ultraviolet catastrophe? The ultraviolet catastrophe has to do with the calculation of the radiant energy of a black body that is radiating. So, according to classical, statistical mechanics, and you don't have to know a lot of statistical mechanics to be able to derive this. I will do this for you. According to classical statistical mechanics, if you compute the the radiation that is emitted by a black body which is heated up, to a certain temperature, then the result you get implies that the radiation density should diverge, that is become infinite, as at the high end of the spectrum. Okay, and because it's on the high end, that is on the ultraviolet end, and because what it's saying is that at the ultraviolet end, you should expect the energy given out by this object to be infinite, and which is clearly not a physical result, right? And that's why this was called the ultraviolet catastrophe. You guys know the meaning of the term catastrophe? It means a disaster. Okay. Okay. So,
sir.
Yeah.
Did it have to be a black body? Like, does the property have something to do with it, or we can use other sort of color?
You can use other bodies, but the analysis would be just unnecessarily complicated.
Oh, okay.
This would be a generic feature, and it's easier to deal with the black body. That's why.
Oh,
so it would transfer to other bodies, not just the idealized one.
Sorry?
So it would transfer over to and apply for other bodies, not just idealized black bodies. Is that the case?
Exactly. Yeah, exactly. Yeah. So the formula that classical, statistical mechanics gives you is known as the Rayleigh Jeans formula. It's two people. And so what we will do is that we will first derive the Rayleigh Jeans formula, okay? So let's just first start with a black body. Okay, what is a black body? So what do you think is a black body?
Perfect emitter and absorber of radiation.
Perfect absorber of radiation. Yes. It is also turns out to be a perfect emitter. So black body is a body which absorbs any radiation that is incident on it. Okay, it absorbs any radiation that is incident on it. Okay, so experimentally, how do we build black body? The way to build a black body experimentally is to take a chamber, a thick chamber, which has a very small opening. Okay, so I'm just gonna use a bit of a thick pen to emphasize that the walls of the chamber has some width. Of course, this is a cutaway diagram. Okay. All right. So, so this is a chamber, and now see that. Suppose that a radiation enters the chamber. Okay. Maybe not use such a thick. Yeah. Suppose that a radiation enters the chamber through the little opening. Then it's very unlikely that this radiation will be able to get out of the same opening, because first the radiation will bounce around, right? And as it bounces around, at some point it'll get absorbed. Okay. Suppose after 2 bounces it gets absorbed. So this is how you construct a black body. You can ensure that any radiation that enters this body, this cavity, is absorbed. Okay.
So the sun is also approximated to be a black body.
Yeah, it turns out that many objects which yeah, that's an approximation, and that's not an exact approximation. It turns out that the Big Bang, that is also can be approximated as a black body. Okay, the spectrum of the Big Bang. So it's a very, very useful concept, the black body radiation. Okay, so
I want to ask something, like
yeah,
as the question of sun came up. So if sun is considered as some approximated as some form of black body, like we know that sun emits certain wavelengths of light at a higher intensity compared to some other wavelengths, like yellow region of wavelength is emitted with more intensity than any other region of light. So is it an issue, like, because other wavelengths are not as that much intense as some other waves? So does it contradict with the definition of black body or something?
no, it doesn't. It doesn't. As you'll see that, this is I'm just describing to you what the definition of how to create an experimental black body, right? But you will see that when you heat up a black body, it actually emits radiation in all the different wavelength, but it does not emit radiation with the same intensity at each of the wavelength. The intensity is different. Okay.
Okay, sir, I got it.
Okay. Okay. So when such a black body is heated up, okay. So when a black body is heated up to a certain temperature, the resulting spectrum has a very characteristic shape. Okay? the resulting spectrum has a characteristic shape. Which is determined by the temperature. Now, what does this shape look like? So instead of me trying to draw this shape, let me just show you a picture. So this is the picture, okay? So here we have, on the x-axis, we have the wavelength, and on the y-axis, we have the intensity in some arbitrary units. And as you can see, is that, for a given temperature, each of these curve is given for a given temperature. So this is for, say, 6,000 Kelvin, this is 5,000 Kelvin, 4,000, 3,000, so on and so forth. That, as the wavelength increases, there you reach, the intensity increases until you reach a maximum, and then the intensity decreases and slowly asymptotes to zero. Okay, so as you can see, this is not a the object is radiating with different intensity at different wavelength or frequencies. Okay. All right. So, that curve that I just showed you was the experimental curve of a black body radiation. So as theorists, what we should try to do is that we should try to derive that curve from classical statistical mechanics.